So the next chapter that we want to look at is a chapter involving what we call chemical kinetics, or I suppose in one sense chemical speed. Okay, how quickly does something happen? And I guess if you're talking about how quickly something happens, I'm going to give you an analogy. I'm going to give you the analogy of speed. Okay, now from your junior cert, I hope you remember that speed equals distance over time. How far and over how many seconds or how many minutes or how many hours. Okay, the chemical kinetics we're about to study here now has more or less the same approach, except we're going to be looking at the rate is equal to the quantity formed over the time taken. Okay, so it has the same approach, and I want you to think all the time about the analogy of the car. Okay, traveling a certain distance over a certain time. That's how we calculate the speed of a car. A chemical reaction is the quantity of a chemical or a product that is produced over the time taken to produce it. Now, there are other ways of measuring chemical reaction rates, which I'll talk about in a few moments. It doesn't always have to be about measuring the production of something. It can be about measuring the loss of something, or it can be about measuring how quickly we lose sight of something. Okay, so there are three ways that we're going to explore in this chapter as to how to measure how quickly a reaction takes place. So we call the speed of a chemical reaction the rate of a chemical reaction. All right, and the two things involved in rate are quantity and time. Quantity and time. That's the key thing. All right, and if you keep those two before you, then you'll always be able to calculate what we call the average rate of a chemical reaction. The rate or the speed of a reaction is a measure of how quickly a reaction happens. So we're measuring. Right? That's the key thing, and we've got to come up with ways by which to measure either the production of A, the loss of B, or the transparency in a liquid. Because sometimes when a chemical reaction occurs, the liquid can go from being clear to being cloudy, so we're losing the ability to see through it. And when we get to a certain point when we cannot see through it anymore, that could also give us a good measure as to how long it took us to get to a certain point. Some reactions, like explosions, are very quick and they're instant. Okay, they finish within seconds. Some reactions, like rusting, are very, very slow, and they finish in months or indeed years. Now, we all know what happens when we get the dreaded scratch on the car. Okay, you get a scratch on the car, you stand back and look at it, you think, it's okay. Then after a week you notice, it looks okay. Then after a month you kind of say it's not okay. Then after a year the door falls off. Okay, well, maybe not as dramatic as that, but you get the idea. Okay, it takes a long time to do a little chemistry. But the chemistry, unfortunately, in rust is irreversible. It can't undo the damage, okay? It has to be, the iron involved has to be replaced. Some reactions, of course, like baking a cake, are somewhere in between. So it's like Goldilocks and the Three Bears, all right? Too quick, too slow, and just right. So you have your explosions very, very quickly. You've got your rusting, which is very, very slow. And then you've got your baking of the old Christmas cake, which is somewhere in between. You can smell it happening. You know it's going to happen, but you still got to wait, okay? So although reactions are classified as being slow or being quick or being somewhere in between, the rate of a chemical reaction is measured in the same way. So it doesn't matter what chemical reaction we're undergoing. You will measure the rate of the chemical reaction in the same way. And I hear you ask, how do I measure it? The answer is you'll be measuring quantity, whether it's a gain or a loss, over the time taken to gain or to lose. That's it, okay? So it's the quantity that you're losing or gaining over the time taken to lose that quantity or gain that quantity. The rate of a reaction, and this is the definition because it's all in red, so this is something that can be asked in the exam. The rate of a chemical reaction is defined as the change in concentration of a reactant or a product per unit time. Now that's great, because if I take A plus B and gives C plus D as a chemical reaction, there are four things I can measure. I can measure, now don't forget A and B will be used up, so I could look at how A and B are depleting. I could watch them disappear, or I could watch C appear and D appear and try to measure either the dropping concentration of the reactants or the increasing concentration of the products, okay? Or put another way, the decreasing mass of the reactants and the increasing mass of the products. Or even another way, the decreasing volume of the reactants and the increasing volume of the products. So we really have to find out what's the best way to measure any one of these four quantities in this thing here. So if you're asked for the definition of what is the rate of a chemical reaction, it's defined as the change in concentration of either the product or the reactant per unit time. And that's extremely important, per unit time. And if I was to ask you straight off, what is the chemical unit of time? What do we use in chemistry when we're measuring rates of reaction? The answer is always the second. You're not going to be measuring in minutes. You're certainly not going to be measuring in hours. You are going to be measuring in seconds. So it's very, very important that we'll always have some type of a stopwatch like that in order to be able to measure the reactions in seconds. Okay, so stopwatches are going to be an essential piece of kit as we go forward. Concentration that we're measuring, whether it be an increase or a decrease, will be in moles per litre. And time, as I told you already, will be in seconds. So that's what we're looking at. Now, you don't just have to measure concentration. You could also measure volume in centimetres cubed, or you could measure mass in grams. But as long as you have a quantity that you can measure, then you hang on to that, and you see how that quantity changes as time ticks by. That's the essence of this chapter here. There are many ways, as I told you already, to measure the rate of a chemical reaction. Number one, we could measure the production of a gas over time. Now, if you're producing a gas and you want to measure it, you're going to have to trap it, okay? And you trap it in a container that has measurements on it, namely a large graduated cylinder. So you could trap a gas in there and you could see how much of that gas is being produced over a certain amount of time. Secondly, you could simply measure the loss in mass of a substance over time. And thirdly, you could measure the amount of light that's able to pass through. So if light is able to pass through no bother at the beginning when the solution is clear, we could simply time how long it takes for the light to stop coming through when the solution gets cloudy. All right, and each of these three will be examined as we go through this chapter. A stopwatch will be an essential piece of kit because that is how you measure time. Now, you can use the stopwatches in the lab or you can use your mobile phone. Whatever way you know how to use a stopwatch, use it. If you're familiar with your mobile phone stopwatch, that's what I will ask you to use because I want you to be familiar with how to start it and stop it and so on. So here's a typical experiment that we would do if we were in school, and we will do when we go back. It's an experiment to monitor the rate of oxygen production from hydrogen peroxide using manganese dioxide as a catalyst. Now, I hope you remember this word here from your junior cert. A catalyst is any substance that changes the speed of a chemical reaction. There are catalysts that will increase the rate. There are catalysts that will decrease the rate. So you're not allowed to say anymore, a catalyst is a substance that speeds up a chemical reaction. No. I would much prefer you say a catalyst is a substance that alters the rate of a chemical reaction. Don't say what way it's going, just say that a catalyst has the ability to change the rate of a chemical reaction. Okay? And the experiment involved is exactly as you see here. So you've got a conical flask with a side arm. You've got what's called a delivery tube. So that thing there is a delivery tube. And it's extremely important in these experiments that you label everything. Okay? This is a conical flask. Then this is an inverted grad cylinder. And this thing here is your stopwatch. Now, the trough, this is called a trough. When we're using a large basin of water, we want to sound posh. We don't say we're using a basin. We say we're using a trough, okay? And it's not a trough that pigs feed out of. It's a trough that simply holds water for chemical experiments. Okay, now, notice what's happening here. And you're probably going to ask yourself, what the hell is this thing inside that seems to be kind of hanging sideways? That is your manganese dioxide, okay? This is essential because one of the questions they always ask about this experiment is, how do you know when to start the stopwatch? So how do you know when you're at the beginning of this particular experiment? And the answer is very simple. You take a little type of a container like this, small little container, inside which you have your black powder manganese dioxide. That's your catalyst, okay? And then a little string that is simply led to the outside and held in place by the rubber stopper. So when you're ready to go, you take your stopwatch in your hand, you simply lift up very, very gently the stopper until this little container falls in, and then you put the stopper back down again. And all of a sudden what you'll notice is, as soon as that black powder hits the liquid, you're going to see bubbles being given off, okay? Now, in order to be able to measure the liquid, the first thing we have to make sure is that the graduated cylinder doesn't have any more, sorry, did I say measure the liquid? In order to measure the gas, it's not allowed to have any other gases in there. So what we do with the graduated cylinder is we fill it with liquid first, turn it upside down, invert it into the water, take our hand away, and the entire graduated cylinder remains filled with water. Now, if it's filled with water, then it's very, very simple to refill it with air, or any other gas that's being produced. All you have to do is direct the bubbles down underneath the cylinder, and then as the bubbles are produced, they will gather at the top and they will push down the liquid, okay, in a phenomenon that we call downward displacement of water. Now that's what we're using here, downward displacement of water. So I'll say it again. When you begin your experiment, you've got your conical flask with your side arm and your delivery tube into a trough underneath an inverted graduated cylinder. Okay, the catalyst, the manganese dioxide black powder, is held in a little container which is attached by a string to the outside and held in place by the rubber stopper. When you are ready to start the experiment, first of all make sure that your inverted graduated cylinder is filled with water. That simply means there's no other gases in there. When you're ready to start, you then lift up the stopper gently until this falls in, and when it falls in and when you put the stopper down, you start the stopwatch. As soon as the black powder hits the hydrogen peroxide liquid, this is your H2O2 down here, then you'll notice bubbles are going to be formed, and as the bubbles rise up and hit the top, they begin to gather an increase in volume and push the liquid downwards. So we can actually measure, if we're watching here, we can measure what's going on as this level here is being pushed down and pushed down and pushed down. So the bubbles go up and they push the liquid downwards. Now, what we have to do is we have to take the volumes at regular intervals. So normally what we do in the lab is we get the reading of the volume every 15 seconds. So if there's two people working on it, one person has a stopwatch, the other person takes it off, drops in the catalyst, the second person starts, and then every 15 seconds, the person who hasn't got the stopwatch simply shouts out what the volume is that the gas is occupying in the graduated cylinder. Okay, now I have the experiment over here for you. I'm going to send out the slides to you. I want you to watch it. Actually, I'll put the video up on Google Classroom so you can watch it yourselves ahead of time. But I do want you to watch it because they show how the whole thing is set up. So what are we doing? We're starting the reaction by dropping in the manganese dioxide and starting the stopwatch. The bubbles will then begin to come up and gather at the top and push down the liquid. Every 15 seconds, we simply measure how much oxygen, or how much, in this case here oxygen, how much gas has gathered at the top. So as time goes on, and as you get every 15 seconds, you'll notice that the volume is getting bigger. All right. And once you get all your readings, then you build a table. As simple as that. So that's the setup for the practical. Watch the video, please, before you move on. Make sure you can pause this video now, go to Google Classroom, watch the video so that it can show you how this thing happens. And then when you're finished the video, come back to these slides here and back into the video and carry on. Okay, so you've watched the video. You now understand exactly how the procedure takes place. Okay, and again, I'm just going to say it for the fourth or fifth time. You have your conical flask, and dangling in the conical flask a little container of the catalyst, black powder, being held in place by a string and being held by the stopper. Okay, you're standing with your stopwatch, you've got your inverted upside down graduated cylinder filled with water, and you've got your delivery tube ready to go. You lift up the stopper until a little container falls in. When the container falls in, you start and you take the volume readings every 15 seconds. Now the question is, how do you know when to stop? Are you going to be taking volume readings every 15 seconds for the next 3 weeks? Obviously not. There's a finite amount of chemicals, so therefore there's a finite chemical reaction going to take place. When you keep your chemicals nice and small, then eventually something's going to run out, okay? You don't have an infinite amount of hydrogen peroxide, you've got a finite amount. So you will reach an end. And the key thing to understand is, how do I know when the experiment is over? How do I know when this reaction has ceased? And I want you to take a look at the table here, okay? Now, obviously, we're going to be doing this one first of all. We're going to be doing time versus volume. I'll come back to this in a moment. So I want you to take a look at this. Here's a table. So I started my experiment. I lifted up my little rubber stopper. I allowed in the manganese dioxide, and I started the stopwatch, okay? And here, every 15 seconds, I simply recorded how much oxygen was being produced in the graduated cylinder. Now, take a look at the volume, and particularly look at the volume at the end, and it becomes very, very clear how you know when the experiment is over. Starting at the beginning of your experiment, you're not going to have any bubbles, okay? That's fine. After the first 15 seconds, you collected 60 centimeters cubed of oxygen. After 30 seconds, 110 centimeters cubed. After 60, 150. After 150, 193. Now watch what happens next. After 3 minutes, that's 180 seconds. After 3 minutes, you have 197 centimeters cubed of oxygen. After 210 seconds, you have 200 centimeters cubed of oxygen. And after a further 40 seconds, you still only have 200. Now, what does that tell me? Doesn't that tell me that there's no further oxygen production? So therefore, one of the questions they love to ask in the exam is this: at what time did the experiment end? Now, did the experiment end at 240? Well, the answer is no. There was nothing produced between 210 and 240. Nothing was produced. So that means that the experiment ended here. So the first time you hit a repeating volume is the time that you call the reaction over, finished, kaput. Okay, so this is where it finished. After 210 seconds, I had 200 centimeters cubed. In a further 30 seconds, nothing else was produced. So you don't use that at all. That's just a sign that we have finished. When we get two readings the same, we know we're definitely finished. But the finishing mark occurs at the point where the first of the repeating volumes happens to be recorded. Okay, now what do we do with these readings? Well, obviously, when you've got a table like this, go to your maths. When you've got a table like this, the only thing that we can do when you're comparing two sets of values, in this case time and volume, is to plot them on the XY axis. And when you do that and you put them onto the XY axis, you will end up with a graph. Okay, but there's a couple of things I want to talk about in terms of a graph. In chemistry, graphs are brilliant ways of picking up huge marks very, very quickly. They are also ways in which you can lose huge marks by making silly omissions. Now take this page here on these slides as being your gospel for graphs, okay? The first thing you've got to do is always put time on the x-axis. Time always goes on the horizontal, okay? And then you put the other quantity on the vertical axis. In this case here, we're measuring volume versus time. So time on the x-axis, volume on the y-axis. That's the first thing. Secondly, please label both of your axes. Tell me what the numbers on the horizontal represent. Just write down time in seconds underneath them. Tell me what the values on the y-axis represent. Volume in centimeters cubed. Okay? You're not just going to draw a y and an x-axis, put the numbers in, draw the graph and leave it, because that could be the graph of anything. I need to know what are the two quantities that you are comparing. And if you don't label your x's, you lose a huge amount of marks. Okay. Finally, plot and draw your curve as carefully as possible. So plot your points very, very carefully. You really do have to pay attention when you're plotting your points. It's so easy to put a point in the wrong place. So you pay attention, plot your points, and then as carefully as you can, get the best curve through those points as you're able to. So you should end up with something that looks like this. Okay, so if I was just to go back here to these values, so I'm going to take these values here. Now, I'm not going to leave out the last one, obviously, but I just know that's where it finishes, okay? But I am going to put in on the time axis, I'm going to go from 0 all the way to 240. And then on the vertical axis, I'm going to put the volume from 0 to 200, okay? And when I do that, I get something like this. Now, there's your 0, 0, and notice that the last two readings are the same. So when you get to 210, you get 200 centimeters cubed. When you get to 240, you get 200 centimeters cubed. So when it flatlines, when a graph flatlines, reaction is over. But this here is not where the reaction ends. The reaction ends when you hit the beginning of the flat line. So there's the finish on your graph, okay? And your finish, as you can see there, is, as we know already, halfway between 200 and 220, 210. So you can now use your graph to do a whole heap of things. So if somebody said to you, how much oxygen was produced at 100 seconds? What would you do? How much oxygen is produced at 100 seconds? The first thing I would do is I would go to the time axis. the horizontal one, and I would locate the 100 seconds. And all I've got to do then is to draw towards the graph like this. Okay, and when I hit the graph, take a 90-degree turn out like this, and that, where it hits the other axis, is the answer. So after 100 seconds, what did I have? After 100 seconds, I had 150, 60, 75. 175 centimeters cubed. Somebody else might say to you, okay, how long did it take to produce 100 centimeters cubed of oxygen? Now, in that case, you're beginning with volume, so you're starting over here on this axis. How long did it take to produce 100 centimeters cubed? So on the vertical axis, you find your 100 centimeters cubed, you draw to the graph, you hit the graph, and you drop a perpendicular. So every time you hit the graph, you turn 90 degrees, okay? And there's your answer. So in other words, to get 100 centimeters cubed, how long did it take? It took 20, 40, 60. So it took, that's 20, isn't it? So 30 seconds. 20, 40, 60, 80, 100. Yeah, so each box is 20. So it took me exactly 30 seconds to get 100 centimeters cubed. So the beautiful thing about the graph is, not only does it show you in pictorial form what the reaction looks like, it also allows you to extrapolate information. Now, extrapolate means to get information from the graph that wasn't in your table. All right. So, for example, if I wanted to work out the volume of oxygen produced at 100 seconds, I start at 100 seconds, go to the graph, turn 90 degrees, get the answer from the other axis. If I'm asked how much oxygen is, or how long does it take to produce 100 centimeters cubed, I go to the vertical axis to 100 centimeters cubed, draw to the graph, drop a perpendicular, and the answer there, as we said already, was 30 seconds. So you can get information from the graph that is not in your table. Okay. The last thing I want to talk about is the average rate of reaction. So in other words, keep in mind, if somebody said to you, what's your average speed? Now let's say, for example, somebody went from Dublin down to Kerry. Now why did you want to go down there? I haven't a clue. Let's just say, because that's out Healy Ray country. Let's say, thanks Healy Rays. Let's say we want to go from Dublin to Kerry, all right? How long does it take to go from Dublin to Kerry? I don't know. But if somebody says to you, what was your average speed? Average speed, there's two things you've got to remember. You need to know, for speed, you need to know the distance, and you need to know the time taken, okay? So if somebody said to me, oh, it was 320 kilometers and it took me 4 hours. Okay, how do I work out the average speed? The answer is you put the total distance over the time taken, and you do your division, okay? Now, we already know that 4 is 32 goes 8, so my average speed was 80 kilometers per hour. That's your average speed. Now, why am I telling you this in terms of speed? Because you do exactly the same thing in terms of average rate. Because after all, in one sense, the rate is the speed of a given chemical reaction. So let's say, for example, somebody tells me that after 210 seconds, they were able to produce 500 centimeters cubed of oxygen. And then they tell me, what's your average rate? Or they ask me, what's your average rate? Well, the average rate is equal to the quantity produced over the time taken. Now, what did I produce? I produced 500 centimeters cubed. How long did it take to do it? 210 seconds. So therefore, 500 centimeters cubed in 210 seconds. What's my average rate of reaction? Go back to this. 500 divided by 210, and that comes out as 2.38. Now, be careful. What are the units? The units are centimeters cubed per second. cm cubed / s. So again, I want you to go back to the model of the car. If you want to find out the average speed, get the distance, get the time. If you want to work out the average rate of reaction for a chemical reaction, get the quantity and put it over the time. Okay? And your units for average rate of reaction will always be centimeters cubed per second if you're using volume, or it might be grams per second, or it might be whatever light units are, lumens per minute, or whatever it's going to be. Okay? But in this case here, because we're using quantity and time, it is centimeters cubed over seconds, because we were measuring volume. Okay, now the average rate of reaction is calculated by dividing the total volume by the total time. So in this case here, rate equals the volume over the time. All right. So in other words, time will always be the one you're dividing in. The one on the top might be volume, might be mass, might be lumens, might be anything. Top one can change, but the bottom one will always be time. So let's take this table here. Now this is, just wanted to look at this carefully. This is the same table we had a minute ago. Okay, first of all, if somebody said to me, here's a table, calculate the average rate of reaction, what would I do? Well, I'd say the following. Average rate of reaction is equal to the total volume, because don't forget we are dealing with volume, the total volume over the time taken. Now this is where you have to be careful. First of all, what's the total volume of oxygen produced? Well, just run along the bottom line. The total volume of oxygen produced is 200 centimeters cubed. Now here's the key thing. How long did it take to produce 200 centimeters cubed? When was my reaction finished? Was it finished here or was it finished here? And the answer is your reaction is finished the first time you hit a repeating volume. So notice 200 repeats itself here. So therefore the finish is that one. So it took 210 seconds to produce the total volume of 200 centimeters cubed. It's not that one. We don't use that in our calculations at all. We may plot it as part of a graph, but never as part of our calculations. So then you get your 200 over 210. So 200 divided by 210. And in this case here, you get an answer of 0.95 centimeters cubed per second as your average rate of reaction. Okay. Now, let's just, I think I have that printed here as far as I know. Whoops, right? Yeah. In the case of the above table, we see that this being the finish, what does it tell me? 200 centimeters cubed formed in 210 seconds. So you put the quantity, 200, over the time. Time is always on the bottom of your fraction. And as I said already, that will give you the 200 divided by the 210, which is 0.95. Now I'm going to stop there because I want you now to go and do two questions. I want you to plot your graphs. And when you've plotted your graphs, I want you to go to Google Classroom, I want you to scan them, and I want you to upload them with the answers to the questions that follow, because I want to see your graphs. Use graph paper. Don't do these on lined paper. Graph paper, nice big graphs, properly labeled axes, nicely plotted points, and a lovely curve through those points. And then underneath the graph, I want you to write down the answers to the questions. So here's your first one, define rate of reaction. Then it gives you a table. The table says plot a graph, and then it asks you a question, after how many seconds did the reaction end? And lastly, calculate the average rate of reaction. That's your first question. And the second question then is this one here. Again, another table where they ask you to plot a graph. Then they ask you to use your graph to determine how much oxygen was produced in the first 2.5 minutes. Now, if you're not too sure how to do that, go back over the video because I did do 2 examples on that one. And lastly then, you calculate the average rate of reaction. So off you go back to the 2 questions, get them done, put them on paper, scan them, the graph and the answers, and you're going to upload them to Google Classroom where I can see them, correct them and send them back to you just in case I need to tweak or tell you about anything that mightn't be correct on your graphs and in your answers.